Hello, welcome to a massive open online course on fluid flow operations. So, this is the lecture number 33 as module 12. In this lecture, we will discuss more about that multi-phase flow phenomena and its application. And finally, we are having here the applications of multi-phase flow phenomena. So, in this lecture, we will include the different applications of like gas liquid flow, gas solid flow and gas liquid solid flow. What are those applications that are being actually processed in industry for different yield. Now, let us consider the application for gas liquid flow. So, you know that there are several pattern of the multi-phase flow. For the gas liquid flow, we got like bubbly flow, slag flow, plug flow, even stratified flow, wavy stratified flow, mist flow. So, one of the important flow pattern out of those flow patterns is called bubbly flow. Now, what are the applications of that bubbly flow? Now, if we consider the absorption of carbon dioxide or any suppose pollutant gas in atmosphere. So, how to actually reduce those gases by this two phase bubbly flow system. Now, in this case, let us consider that carbon dioxide which is most important aspects of environmental concerns that carbon dioxide to be removed anyway. So, based on that there are several actually process are being developed, even going research on that particular field, how to absorb that carbon dioxide or remove that carbon dioxide from the atmosphere. So, as a two phase bubbly flow systems, how actually the process is being developed for the absorption of carbon dioxide in a liquid medium. So, in this case, if we see here in the slides that that one actually process unit, it is called gas liquid unit, and it is especially named as bubble column. So, in this case, how these bubble column bubbly flow systems are being used for absorption of carbon dioxide. Before going to talk about that, let us consider that carbon dioxide gas where actually can be absorbed. Of course, there will be some solubility of this carbon dioxide, optimized solubility of that carbon dioxide in certain solution or solvent. So, this carbon dioxide gas as per solubility you cannot absorb in simple water. So, in this case you can apply, you can use different types of solvents to absorb this carbon dioxide. One of the important solvent is called monoethanol amine, and some other solutions like ammonia solution, potassium carbonate, sodium hydroxide, even nowadays ionic liquids also are the mostly used studied scrubbing solvents for this carbon dioxide absorption. Now, in that case you will see with those the solvents more than 90% of the carbon dioxide can be removed from the atmosphere, and in laboratory scale it is achieved at methyl ethyl amine and to carbon dioxide ratio of 2:1 or even 1:1 when other amines such as diethylamine is used. And for that some chemicals sometimes being added to increase the efficiency of the absorption. In that case piperazine denoted by PZ is one of the widely studied chemicals that is added into the solution in order to increase the absorption reactivity. Even nowadays magnesium hydroxide, environmentally friendly and regenerable adsorbent is also attractive to use for the absorption of carbon dioxide. Now, how then the process is actually carried out for this carbon dioxide gas absorption in two phase bubbly flow system. So, let us consider here that column here, and in this column at the bottom side you will see one distributor, gas distributor. It is sometimes called spudger, and which is made of a plate of n number of holes, which is specially arranged, whether this triangular arranged or square arranged, or sometimes some distributor will be used as a nozzle systems through which gas will be coming into the column, and the gas will be dispersed as a dispersed phase of bubbles in the column. So, in this case, if we consider that from the cylinder of carbon dioxide and along with nitrogen, if it is coming into the what is that column through the spudger as a dispersed phase of bubbles in a solvent. Now, solvent may be that either of the solvent, methyl, ethyl acetone or ammonia solution or potassium carbonate, here it is given in the list. So, either solution you can use. So, in the solution then carbon dioxide gas that is taken from the atmosphere by blower or by suppose carbon dioxide from the cylinder, if you pass it, what will happen through the distributor, it will be dispersed in the solvent as a dispersed phase of bubbles. Now, whenever the bubbles will be forming, what you will observe? You will see that there will be a formation of interface between this bubble and the liquid. So, through the interface there will be a transfer of the carbon dioxide molecules to the liquid. So, here there is a mass transfer, it is called mass transfer, whenever carbon dioxide gas molecules is transferring from the carbon dioxide gas bubbles to the liquid solvent. So, it is called mass transfer, and there will be a interface and through which these molecules will be crossed, and there will be a resistance of this interface, and upon considering all those resistances there will be a some coefficient or factor for which there will be a transfer of these molecules. Now, what is that factor? It is called concentration gradient. You will see there will be a carbon dioxide gas molecules that will be in the surface of the molecules, surface of the bubbles or interfaces. Then what is the concentration there at the interface, and what is the concentration of carbon dioxide molecules or gas in the bulk liquid or in the solvent initially. So, if there is a concentration gradient, you will see there will be a driving force of transferring of molecules from the carbon dioxide gas bubbles to the liquid, and this concentration differences will give you the efficiency of that mass transfer happen. Now, in this case this transfer molecules, number of molecules, or you can say the flux of the molecules, that is flux means per unit, that is mole of that is gas or carbon dioxide transferred to the liquid per unit time, per unit cross sectional area or per unit area, unit surface area. So, it will be called as a flux. So, that flux will be actually proportional to that driving force of concentration differences. So, and that proportionality constant, it is called overall mass transfer coefficient. Now, this overall mass transfer coefficient actually based on the concentration in the bulk of the carbon dioxide bubble and the concentration at the what is that bulk of the solvent. So, there will be a concentration differences at bulk of the carbon dioxide gas and to the bulk of the liquid. So, that is a overall mass transfer coefficient. If suppose there is a concentration difference, if you are considering that from the interface to its equilibrium concentration of that carbon dioxide molecule, then you will get that individual mass transfer coefficient there for the gas, and also for the liquid also there will be a increase of concentration of carbon dioxide from its beginning to the what is that final equilibrium stage. So, there will be a concentration gradient. So, if you are considering that concentration differences in the gas as well as liquid individually, then you can obtain based on that theory of that is diffusion or mass transfer, then you will be having that what is that individual mass transfer coefficient. If you are considering that the bulk concentration of the carbon dioxide and bulk concentration in the liquid and the difference is as a driving force, then it will be called the overall mass transfer coefficient. Now, this overall mass transfer coefficient actually depends on the interfacial area. So, that is why carbon dioxide gas is being supplied through the liquid as it is first phase of bubbles, where you can get more interfacial area. So, in this interfacial, through this interface there will be a mass transfer area. So, this is the process by which you can absorb this carbon dioxide gas from the gas to the liquid, gas mixture to the liquid. So, this is the mechanism here, how this absorption of this carbon dioxide being happened. And if you are considering this is only physical absorption, then there will be no reaction, then in that case only simple carbon dioxide molecules will be in the liquid or absorption. Now, if there is a reaction that parallelly the carbon dioxide with some other amine solutions there is a reaction, then what will be that? Maybe sodium hydroxide, sodium carbonate will form, or other carbonate form will form in the organic medium, then you can say that that will be reactive mass transfer there. So, in that case also this interfacial area is very important. So, to get this interfacial area, you are making the carbon dioxide gas bubbles to get more mass transfer there. Now, question is that why should make this bubble without just you can supply the carbon dioxide gas in a column in the core region, in the central region from the bottom, and if you supply the liquid from the top of the column, that is called weighted column, you can get also in surface area, but the surface area will not be enough to get the more mass transfer compared to this bubbling system. So, that is why the two phase bubbling system, as here as an example of carbon dioxide gas absorption, that is one important process. Even some other several processes in bubbling systems also happen, not only carbon dioxide gas absorption, you can apply it for other Cox gas, NOx gas also you can apply based on this principle. So, this is one example that is for multi-phase systems. So, here generally in this system typically you can say that solvent concentration generally 0.05 to 1 mole per liter is being considered, and temperature is 293 to 303 K for DEA, that is diethylamine, and column diameter typically you can also scale up this column diameter, that is typical one, that column diameter 0.06 into 0.06 meter, a rectangular column you can make, or even cylindrical column also you can use. So, there are several studies, there are several research components also here to increase that mass transfer efficiency. Sometimes if you produce more finer bubbles of carbon dioxide, then you can get more surface area, then you can have more mass transfer efficiency there. So, more carbon dioxide gas within a less time. So, what you have to do, that you have to then analyze that how much carbon dioxide is being absorbed, that is being done by that carbon dioxide gas analyzer by mass balance, and also if you analyze that liquid sample, how much carbon dioxide gas is dissolved in liquid, that you can measure, and also some other parameters, what should be the flow rate of that carbon dioxide gas, and if you change the gas flow rate, you will see your hold up of this gas will be more, and that hold up of the gas will give you more surface area, because we have already studied in our previous lecture that that interfacial area, specific interfacial area is depending on the gas hold up, and that is actually estimated by that 6 into epsilon g by diameter of the bubble there. So, based on which we can say that if we produce more finer bubbles, more interfacial area will be produced, and in that case more mass transfer can be observed. So, one of the important variables here is gas flow rate. If you increase the gas flow rate, you can get more hold up. Even another important physical properties of the liquid like this, if you are using a different type of solvent based on their physical properties, accordingly the gas hold up and mass transfer efficiency will come. Sometimes you know that if you change the pH of the solution may sometimes effect on the absorption capacity. So, this is one important. So, from the bottom you are supplying carbon dioxide, and from the top carbon dioxide gas will be coming out, and then it will be analyzed, and carbon dioxide gas remaining carbon dioxide gas will be coming again to the atmosphere. Even do again BAS of this carbon dioxide, then you can I think reduce more carbon dioxide there. So, this is one process of application of this two phase bubbly flow system. Let us consider another application of bubbling two phase flow. One of the important process like I have called sterilization process. So, in this case the process is generally based on a bubble column using the bubble coalescence inhibition phenomena to produce high bubble densities there. So, here you will see that in this case there will be high bubble densities are produced, and in this case the column will contain hot bubbles that will be ranging in sizes from 1 to 3 millimeter, which rapidly transfer the heat to sterilize water contaminated with biological species at a temperature up to 250 degrees centigrade. So, in this case what you are going to do that you are blowing air, and that before going to that column formation of bubble, what you have to do, you have to clean that air bubble, is there any moisture content or not, and to remove that moisture content you are actually applying the silica gel, and after that through a rotameter, that is air flow meter it is called, through a rotameter you have to pass that gas, and then you are allowing that gas through a gas heater to heat up that gas at a certain temperature. At that temperature it will be passed through the what is that column, and that is filled with what is that biological species rich water, which will be removed by this sterilization process. Now, if you bubbling this hot air, there you will see there will through the interface there will be heat transfer, and that heat transfer of course will be useful or mainly actually governs this process of this sterilization. So, this is another one important process for this two phase bubbly flow system. Another important application of this two phase bubbly system is desalination of sea water. You will see how to desaline this sea water. You have to remove the salt from this sea water. So, what you have to do, you have to evaporate that water by bubbling systems. So, in this case evaporator bubbling evaporate process with a high temperature gas air, that is flow inlet dried at temperature at more than 150 degrees centigrade, that will be supplied through the liquid medium. So, that the liquid will be evaporated in a column, and that evaporated vapor will be collected and condensed, and it will be collected as a what is that liquid there. So, in that case you will see that sodium chloride solution or other salt, if it is there, it will be actually thickened at the bottom of that column, whereas this moisture or water will be evaporated as this as a moisture, and after then it will be condensed and it will be stored as a liquid there. So, for this the bubbling process is efficient, because in that case the more mass transfer will happen through the surface of this bubble just by what is that, there will be intermixing of the gas and liquid there by this bubbling process, and through the interface of this hot air bubbles there will be efficient heat transfer there. So, based on this there are desalination of the seawater being processed in industry. Now, ammonia removal from wastewater by ozonation process, there are several applications of the wastewater treatment by this two phase system by bubbling systems there. One of the important applications like here we can say that ammonia removal, or what is that arsenic removal, or you can say dye removal by this ozonation process. Now, what is that? Whenever you are going to oxidized by the ozonation process of this ammonia contents in water, what you have to do, you have to make ozone bubbles there, and so that you can get more interfacial area, and then there will be a what is that reaction between these ammonia contents, or oxidation of this ammonia contents, and it will be converted to the ozone derivative products, or what is that other derivatives by this ozonation process. And in the case of ammonia removal, ammonia is decomposed to nitrogen by ozonation process in the presence of bromide. Now, the mechanism of the breakpoint reaction of this ammonia by hypobromide actually is there, and the hypobromide can be continuously produced by ozonation of bromide, and bromide can then be actually utilized repeatedly for further ammonia decomposition. Now, in this case here see one pilot scale bubble column can be constructed, and it can be used for continuous ammonia removal by ozonation in the presence of bromide. And so, here from the bottom here ozonated ozone bubbles will be supplied, and in the column there will be ozone bubbles, and that ozone bubbles by bubbling systems, that there will be reaction, and then you will get the derivative as a nitrogen here ammonia what is that to be decomposed into nitrogen, and then it will be passing out, and then unreacted ozone which will be coming out from the reactor, it will be what is that destructed by ozone destructor, and it will happen at a certain pH value, and that you have to actually allow the sodium hydroxide there to control the pH there. So, at a certain pH you can get the optimized value of this decomposition of the ammonia, and generally the ammonia smell will be in the liquid. So, to remove that ammonia smell, generally this ozone gas is supplied there to get the advanced oxidation of this ozone to decompose this ammonia. Another example, like suppose arsenic removal, what you have to do, you will see that in groundwater there are several regions in India, even in other neighbor countries, the arsenic rich groundwater there. Now, how to remove that arsenic by this two phase bubbly flow systems? In this case, generally groundwater, the arsenic is stated as a arsenic 3 compound. So, in that case you have to convert this arsenic 3 to arsenic 5, because the arsenic 3 cannot be removed by any adsorption process, whereas arsenic 5 is easier to adsorb in a certain adsorbent. So, generally this arsenic 3 is initially converted to arsenic 5 by this ozonation process. Now, in that case you have to supply the ozone bubbles to convert this arsenic 3 to arsenic 5, and whenever this arsenic 5 is being converted, and it will be then adsorbed into a adsorption suitable adsorbent, then in this way you can remove the arsenic from the groundwater. So, this is also one example of this bubbling flow system. So, here the ozone gas to be supplied, not only here simple gas cannot be possible to supply. So, you have to supply as a bubbling system. So, that is why bubbling bed, or you can say that is two phase bubbly or bubbly flow system, that is applied for these particular processes there. Now, another example, decolorization of the dye in textile wastewater. You will see decolorization of the wastewater that contains direct dye stuff, and you can remove that color, that is sometimes it is called what is that Sirius blue, SBRR, or other several dyes also they are different colors. So, to remove that you have to do this decolorization by ozonation process. Now, in this case if you colored dye is being processed by these ozone bubbles, maybe micro bubble systems, even sometimes conventional bubbling systems, you will see after a certain time whatever dye compound are there, it will be actually degraded and it will be converted to colorless, and then you can say that the advanced oxidation of ozone by these bubbling systems will be effective for this particular process, and it will happen for a particular pH value, whether it will be acid or basic medium. That is important to know. Generally, the colorization of this dye process is being happened, and it optimized at basic medium around pH will be equals to 12, and the dye concentration time data during decolorization can be analyzed, that is by spectrophotometrically, and the dye named, that is commercially serious blue, SBRR, that is direct blue 71 it is called, and the chemical formula is given here in the slides, generally present in textile wastewater. To now the reduction of the absorbance of this direct dye stuff wastewater can be achieved around 97.4% after 26 minutes of the reaction with ozone. So, that is one important application of this ozonation process, that is called two phase system, two phase application. And another process, it is called de-inking process by two phase mixing. Sometimes you know that paper industry, they are removing that what is that ink from that waste paper, and then they are reprocessing it to make further paper there. So, in that case recovered paper is generally disintegrated in water based solution, and the principal chemicals here is generally being used in the pulp as a sodium hydroxide and hydrogen peroxide there. It will be a gradient to actually advanced oxidation process. In this case the pH adjustment to about 9 to 10 with sodium hydroxide to make pulp at a temperature of 40 to 45 degrees centigrade, and this happened for this mixing process just by bubbling system and by air, bubbling by air. So, air is just passed into the reactors, and in that case liquid mixing time is one important factor to actually make it efficient process, and in that case how to actually calculate that mixing time, that is generally by residence time distribution technique, by which you can get how long actually the liquid will be residing inside the column, that is important there. So, that will be denoted by the mixing time. So, in that case one important that is qualitative index, it is called mixing time, frequently used to represent overall mixing property in the reactors. And after specific times of this what is that flotation of the paper in a column to remove that ink, generally up to 30 minutes, the de-inked pulp obtained from flotation step is carefully washed by tap water there, and the de-inked pulp is then set to dry overnight after screening and processing the final pulp by hand. So, in that case you will see after processing by this flotation techniques of this paper with a certain minute, at a certain minute of, that is 10, 20 or 30 minutes, and then what is that you will see those pulp, the color of that pulp will be removing at a certain percentage. Now, more efficient process, of course, it will enhance that removal of color. Now, an increase in brightness, or that is removal of colorness to 5% and decrease in number of ink spot to up to 60% can be obtained by changing from a high to low dilution ratio. So, it is very important that how much dilution of this pulp you are being used for this process, because in the column if you are using dense pulp, so in that case it is very difficult to actually float that pulp in the column. So, it is generally being used as a diluted pulp, so that that aeration process from the bottom, that air will be supplied, and in that case aeration process will give you the better mixing, and it may yield more than 60% or even better actually removal of ink, or what is that getting more brightness of the paper, it can happen. So, this is one of the simplest way to actually process the what is that paper, wasted paper, to remove its color and getting its more brightness of this color there. And also another important application of this two phase fluid is called treatment of oily wastewater. Here you will see very interesting that sometimes wastewater contains some oils that is used for certain operations, like suppose grease or what is that for what lubrication purposes, some oils are being used in motor, or even in industry there are huge amount of oil is wasted through a what is that in a particular processes, and it will be left in wastewater. Now how to recover all those oil? Now in that case wastewater of that oily content was actually is pumped through water distributor in a flotation column here in this example. And in that case this effluent with oil rich wastewater is actually supplied from the top of the column, and from the bottom through cyclone systems gas is supplied at its dispersed phase of bubbles. And whenever this oily wastewater is coming in contact with the gas, then you will see that at the surface of the bubbles this oil contents will be attaching, and it will be going up as a floating agents, and then at the top it will be dissolved, and then the oil will be actually making a separate layer at the surface, top surface. And in this case you have to use some frother also to get more oil recovery to get its more efficient process. So in that case you have to select some frother, and you can produce the bubbles in different way also, not a cyclone systems, but other way also you can produce the bubble. Through a spudger also you can use some, but you have to use distributed in such a way that oil should not be clogged in the pores of the spudger. So anyway if you are making efficient spudger, and it will be attached in the bottom part of the column, and through the spudger if you are distributing gas from the bottom part, then as a dispersed phase of bubbles will be coming up, and from the top the wastewater that is reached with oil, and it will be coming downward, and at the counter current operation during that the bubble surface will attach to that oil content, and it will be separated at the top, and then finally you can get how much oil is recovered. You can calculate based on the calculation of initial contents of the oil and final content whatever in the that is solution. So based on which you will be able to calculate, and this is the process is given in this diagram. And in this diagram you can actually study how actually the oil content can be removed efficiently by this spudging process of the bubble. Now practical applications of other plug flow, like about other flow pattern like slug flow, if you are considering that. Nowadays the slug flow in micro channels has paved the way for numerous cost effective and fascinating applications, such as in electronics cooling, in micro mixing of fluid samples, even micro reactors. Sometimes the slug flows are being used there to actually have more efficient reaction and also the yield of the reactions there. And heat transfer enhancement also can be done by the slug flow system. Liquid slug flow has an advantage over gas liquid flow, since liquids in general have higher thermal conductivities than gases. And also you will see for micro channel based heat transfer equipment are being developed nowadays based on the application of the slug flow or advantages of the slug flow in the micro channel system. Another applications is gas solid flow system. This is the heart of this chemical engineering process. You can see there are several applications of the gas solid flow there. If we consider that there is a solid is just floating in a gaseous medium or flowing in a gaseous medium, how then the solid particles will take part or gas solid flow will be actually used for a particular process to get certain yield. Nowadays, whatever power we are actually having here as a what is that electric power, that is actually how it is being processed and how it is actually produced, and that depends on this, you know, that certain application, certain process, and that process is generally gas solid flow. Now, let us consider that it is called coal combustion. Actually, power is produced by what is that combustion of coal. In that case, coal is burning in a system, in a reactor, in a or column, just by fluidizing coal particles there. And in that case, whenever coal is burning, you will see several gases will be producing, and also there will be a what is that a heat generation or heat distribution will be there, and upon that burning processes or producing gas and this will convert that several different other gaseous components which are being used nowadays. You know that propylene, propane, even other products also can be obtained by this coal combustion. And also this coal combustion is being done to produce the steam, and by that steam there will be a what is that useful of the steam to steam turbine for generating this electric power. Now, in this case, generally pulverized coals is being used, and it is being blown through the burners into a combustion chamber. Here it is shown the picture, and where it is fired in suspension. This suspension means coal particles will be suspended in the hot or what is that burnt gas there, or you can say that hot air at high temperature, and then the heat in the flue gas that is exiting the hot cyclone is recovered in series of heat recovery sections of the boiler to produce the steam. So, in this case you can say whenever you are burning the coal, there are several components of the flue gas that is coming together, and that flue gas are so heated that if you supply through a what is that boiler sections, you will see that steam will be boiled and it will be generating that steam, and that steam it will be utilized to rotate that turbine to produce that electricity. So, that is why this is the main process here. Now, this coal combustion chamber, it is called fluidized bed coal combustion bed. So, in this bed you will see whenever coal is burning, there are very several coal particles will be along with coming out with the flue gas. Now, you have to separate that coal particles, small coal particles, and it can be separated by a cyclone separator. In the cyclone separator, due to the centrifugal action, that solid particles will be separated and it will be coming downward, and it may be used again in the combustion chamber. And after separating by this cyclone separator, whenever gas is coming out from the top, and it will be actually utilized in a boiler where the water or liquid will be boiled, and steam will be generated, and that steam will be used in a what is the steam turbine to generate this power. Now, not only by producing this power is generated, sometimes direct flue gas is being used to actually rotate that turbine to produce this power. And also another way that after fluidizing or burning or combustion of this coal, you will see several different type of gaseous components will be coming out in the flue gas. Now, that will be separated, and you can get different products of the gases, and that gas to be actually upgraded into several commercial products. In that case, you may expect that you may get that what is that we are getting whatever we are getting propane, propylene, ethylene, ethyl chloride, even some other organic gases you can have from this coal combustions. Then it will be actually upgraded by different other processes there. So, this is the one way of the producing the power as well as other valuable products of gases from this coal combustion, and this is basically a gas solid flow operation. Another important application of gas solid flow system is called vinyl chloride production. You know that maximum product of our daily things, that pipe, even plastics, goods, all are actually produced by this vinyl chloride, polyethylene or other several monomers also. Now, in this case direct or oxychlorination of hydrocarbons is basically done for this production of vinyl chloride monomer, and from this vinyl chloride monomer you can get the polyethylene different types of products. And then to produce this vinyl chloride monomer from the hydrocarbons, maybe liquid petroleum or maybe from the coal also, you can get this hydrocarbons, and from these hydrocarbons you can produce this what is the vinyl chloride monomer. And how to do that? You have to do the oxidation process now by chlorination. So, it is called oxychlorination of hydrocarbon, and it is generally done for vinyl chloride monomer production. Now, in this case almost 70% of vinyl chloride monomer production can be done via direct chlorination of ethylene at low temperature in presence of iron chloride. So, this is one important process of gas solid operations. So, iron chloride is one catalyst particle. So, in this case ethylene gas and chlorine gas to be supplied at the bottom of the column in presence of what is that iron chloride, and at a certain temperature and pressure, then you can get what is that after oxychlorination in the column in presence of gas solid that is mixing at a certain temperature and pressure, and then you can get that vinyl chloride monomer. After that it will be separated or purified by different processes. So, this is one process of producing vinyl chloride production by gas solid operation. Another important application, polymerization of olefins also it is important. In this case polyethylene to be produced from the ethylene and butene gas. So, in this case ethylene and butene both will be what is that supplied from the bottom of the bed, that is fluidized bed at 70 to 100 degree centigrade and at around 20 atmospheric pressure, and with a certain presence of certain what is that catalyst particles, like you can use that chromium or titanium particles are there. In that case in presence of these particles, this mixture of ethylene and butene, it will be fluidized and in the fluidized column, and then after processing you can get this what is that polyethylene, and after that it will be separated and granulated to a polyethylene and then allowed or passes through further operations there. So, in this case application is simply that gas and solid application. Generally in Union Carbide company they are producing polyethylene based on this concept. This ethylene and butene is fluidized at this 75 to 100 degree centigrade at 20 atmospheric pressure, and the column is designed at height to length ratio is 2.6 to 4.7. So, based on these principles of gas and solid operation, you can produce polyethylene. Now, another application, that is physical operation of gas solid system. Generally it is being used for drying and cooling. What is that? For drying operation, what you have to do, wet solids to be actually placed in a what is that column, and after allowing that hot air from a blower, it will be fluidized in that bed, and after a certain times at a particular temperature, you will see this wet solids or wet material will be dried at a certain time. So, just by evaporating that what is that moisture from the wet material. So, this is basically a physical process of gas solid operation, and it will be fluidized in a column, and to unwanted solid particles which is coming out through the vapor, it will be separated by a cyclone separator, and then solid particles will be used or recycled for further drying processes. So, this is another important process here. So, in this case heat transfer is basically main operation to get the efficient this dryer. So, you have to study the heat transfer, what is the heat transfer coefficient, how the heat is being transferred, what would be the heat duty there, that everything should be known for you. Generally that further actually course for heat transfer operations it will be there. This is the example, just example what are the different processes of different multi-phase flow systems. Now, another important adsorption by solid gas operation here. If you want to remove carbon disulfide from air by activated carbon in a multi-stage fluidized bed, what to do? That you have to supply this carbon disulfide and air mixture in a bed of solid particles of activated carbon, and then at a certain flow rate and at a certain temperature you can remove that carbon disulfide. Even removal of dichloroethane from the fuel gas you can also do it in presence of activated carbon in the fluidized bed operation system of gas solid operation. Even removal of solvents and odd hour materials from air by activated carbon also can be done just by fluidizing the activated carbon particles by air. So, these are the physical application of this gas solid operation. Even you know that urea granulation by gas solid operation, how this urea, that is particulate urea you are obtaining. Generally, whenever urea is being produced, it is coming as a molten urea, that is slug, as a slug it is coming. Now, you have to make that is granular in size. What to do? You have to supply the cold air, that is very near about 2-3 degrees centigrade, that cold air to be supplied from the bottom of the column, and from the top that hot molten urea to be supplied or sprayed from the top. And whenever this droplet of this molten urea is falling downward through this cold air, you will see that hot molten urea, it will be you know that converting to a hard you know that granular urea there. So, this is one application for this gas solid operation, just by fluidizing this urea there, hot molten urea, to make it urea granules. Other several applications like advanced materials here, silicon production for semiconductor and solar industry, even coated nanoparticles, nanocarbon tubes, even sometimes cracking of hydrocarbons like gas phase polymeric reactions here, and also combustion or pyrolysis, combustion or gasification of coal, pyrolysis of wood waste, chemical looping combustion, coating of metal, glass objects, drying of solids, roasting of wood, classifying particles. Even in pharmaceutical industries, you will see coating of pills like tablets, even also granulation process there, production of plants and animal cells, all are actually this fluidization operation based on this gas solid. Even gas liquid solid also, there are some operations there, we will come to that point. Now, if we consider the liquid operation, that is also one type of multi-phase flow operation. Now, if you want to extract some unwanted components from a liquid by another liquid, that will be your liquid operation. Like one example, that citrus essential oil that is being fractionated, or the components unwanted components from this essential oil, that can be actually done by liquid extraction. Now, using a perforated rotating disc contactor, it can be performed. Now, liquid extraction process using this rotating disc and hydrochloric solvents can be easily done efficiently. Now, citrus essential oils are important raw material used generally for formulation of many products that will include soft and alcoholic drinks, even you know that flavoring agents, cosmetics, perfumes and toiletries. So, all those actually applications are there for this citrus essential oils. So in this case there contains sometimes terpenic and hydrocarbons and also oxygenated compounds are there. So you have to remove all those components from this essential oils. So because it will be harmful if you direct use this raw oils there in your maybe skin, even some other that drinks. In that case, if you use this oil directly, that will be your health problem or hazardous for you. So in this case you have to remove those terpenic hydrocarbons, even oxygenated compounds there by liquid extraction. So you have to use some solvent like generally hydrochloric acid generally being used to extract those unwanted compounds there. And this is being done in a what is that rotating disc contactor. Generally the contactor here in this case you will see some disc will be actually baffled in a axial location here in this column as shown here. So whenever it will be rotating, you will see that liquid and liquid solvents and what is that oils will be mixed to each other and making a droplet there, and through the droplet you will see there will be a transfer of what is that unwanted compounds or components from one phase to the another phase, one liquid to the another liquid. So this is called extraction. So based on this process, this separation is being done in liquid operation. Another application, it is called gas liquid solid operation. You will see whatever you will see we are producing some producer gas, even natural, from the natural gas, how to produce that producer gas is there. So from that producer gas we are having different synthesis gases in our daily life. In that case, from the natural gas or steam or some oxidation process, you can convert this natural gas like ammonia or some other things. Then you can directly convert this natural gas to that what is that producer gas, that is mixture of hydrogen and carbon monoxide. And then this hydrogen and carbon monoxide mixture to be actually supplied through a 3-phase system. It is called gas liquid solid system. That is, gas is here mixture of hydrogen carbon monoxide, and it will be supplied to a liquid medium, and that liquid medium will be heated up to a certain temperature by steam, and then it will be converted. After that, this producer gas will be converted at a certain temperature and pressure in presence of some catalyst which will be suspended in a liquid hydrocarbon there. So the syngas is brought in at what is that at the bottom of the vessel and bubbled up through the reactor, and as the bubbles contact the catalyst, the Fischer-Tropsch reaction will be taking place. So basically this synthesis gas of hydrogen or carbon monoxide mixture or producer gas, it will be converted to a several products of that is hydrocarbons like pentene, naphtha, diesel, waxes, and it will be produced just by Fischer-Tropsch synthesis in presence of catalyst. So this catalyst and this the hydrogen and carbon monoxide gas mixture and plus this liquid, that is hydrocarbon, that is the 3-phase mixture will be here in the column. So that is why gas liquid solid operation. Gas is here mixture of hydrogen carbon monoxide, liquid is hydrocarbon, and solid is catalyst particles. So 3 phase will be there, and after mixing at a certain temperature and pressure, and you will see there will be conversion of this synthesis gas to different products like pentane, naphtha, diesel, wax, and then after upgradation of this mixture of this product, you can get several different like separate of this pentane, naphtha, diesel, waxes by hydrocracking, isomerization, reforming and alkylation process there. So this is one important process of this gas liquid solid operation. This is called the slurry bubble column reactor, in which this operation is being done. It is called slurry bubble column reactor. So in this case we are getting then 3-phase system. So I want to stop here, that since we are getting several operations, you can get more than whatever I have shown here you can get more I think chemical engineering, even biochemical engineering processes based on these multi-phase flow systems. And I would suggest you to follow these books, especially here in third one, De Kooning and Levenspiel, fluidization engineering. And these books will be giving you a huge information regarding this gas solid operation. And okay, so thank you for your attention, and I would now actually end of this lecture series here for this particular course like fluid flow operations. So, in this course we have learned the basic understanding of the single phase flow, then multi-phase flow system and its applications. So, I think you will enjoy this course. I would like to wish you for learning this course and enjoying this course. Thank you.